Welcome students to the last video of the week for nuclear chemistry. In this video we're going to talk about nuclear transmutation, changing one nucleus into another. This is the way new synthetic elements are made. We're also going to talk about the kinetics or the speed of nuclear reactions and how that's used sometimes for various purposes. And then we'll talk about some of the health effects of radiation exposure and some of the ways in which nuclear medicine or nuclear chemistry is used in medicine. So the picture you see here is a particle accelerator that's built underground. That's a big, very big circle basically, in which nuclei are accelerated around and around the circle many times until they crash into one another. These things can be quite big. The big one, CERN, I think, in Switzerland, is like a couple kilometers across. It's very big. They need these kinds of distances to accelerate these nuclei fast enough so that when they crash together, they can fuse just momentarily for a tiny fraction of a second, so that they can say, we made a new element and kind of study it a little bit, but it doesn't stick around for very long. So how does nuclear transmutation work, and how could we solve a nuclear transmutation type problem? Oops, let's look at one like this. So this is the kind of problem I would present to you in terms of nuclear transmutation. I'll give you all of the reactants or products except for one, and say, well, what would be produced in this situation here? So here we have an example of a nuclear transmutation. Bismuth is being crashed into chromium, and what is produced is a new element and a neutron. So let's go ahead and try to find the atomic numbers here for bismuth and chromium. We'll need them. Whoops. And so we'll look for bismuth here. Bismuth is element 83. Bismuth is element 83. And chromium is element 24. So bismuth is element 83. Chromium is element 24. Okay. So let's write those in. This is element 83. Chromium is element 24. And a neutron has 0 charge. And so just like before, when we're doing these, we need to make sure that both sides add up to the same thing in terms of mass numbers and in terms of atomic numbers. So if we're doing mass numbers on the left here, so for our A, or our mass number, this is going to be on the left side here, 209 plus 54. So on the left side, our mass numbers add up to 263. And our atomic numbers, Z, are 83 plus 24. They add up to 107. So on the right side, what we need something for the atomic number that adds to 0 to make 107. Well, x plus 0 equals 107, so x equals 107. So we must have element 107 that was being made here. And in terms of the atomic numbers, the mass numbers rather, we got the atomic numbers. We need something here, right up here, that adds with 1 for the neutron, and will add up to what we have over here, 263. So this x must equal 262. So this is going to be 262. And so now we'd have to figure out which element that is. I've got my desktop audio turned down. There we go. This will be better. Okay. You won't hear that ding so loud. Let's now look, what is element 107? So we look at our periodic table here. We're looking for element 107. We'll find it down here. It is BH, or borium. This is named after the scientist Niels Bohr, who was one of the first to discover some of the inner workings of the atom and quantum mechanics. And so we're going to now write the symbol next to it. It is borium, BH. Okay. So that's how you do a nuclear transmutation problem. I've got another one here. Curium, okay, Cm, and helium. So we'll want to look at the periodic table for these two. Helium, we already know it. You probably have that one memorized. It's 2 here, or N is 0 for a neutron. Let's find out what the atomic number is for curium. Curium is down here in the actinides. And so it is element 96. Its atomic number is 96. And so we're going to put that in right here. I'm going to put 96 down right in here. 96. Okay. And so now we'll do the same thing. We got to figure out what the atomic numbers add up to. Or sorry, the mass numbers, A. So this is going to be 242 plus 4. Those add up to 246 here. And then we'll do this also for the atomic numbers. So we have 96 plus 2. This is 98. Now remember, we're following the same rules we did before for writing nuclear equations, is that all of the mass numbers on one side have to add up to the same as those on the other side, and all the atomic numbers have to. So what this means is for the mass numbers here, we need something which we can call x, which adds to 1 and makes 246. So x here must be 245. So 245 plus 1, the 1 here, adds up to 246. And likewise, we need something here which adds to 0. So for z, we have something, okay, what, which I'm going to call it y, plus 0 equals 98. Well, obviously, y is 98 here. So 98. So we just have to figure out what element is element 98 now. We go to our periodic table, look for element 98. It's 2 over. It's californium, CF. They have some funny names for these elements, huh? So these are synthetic elements again. Oh no. I went all the way back to the beginning. Okay. And so what state was the it was California. I forgot to write the. And what state was the element made in? You can probably guess California. Like many synthetic elements, there's americium too. There's berkelium. Those were all made at the particle collider at the National Lab in Berkeley, the Lawrence Livermore National Lab. And so this was obviously made in California. Again, these are for general science interests. They don't stick around very long. They're highly unstable, but it's very interesting that they can be made in these particle accelerators. Whoops. So now we're going to talk about measuring radioactivity and its impacts on health. The way radioactivity is measured is by the use of what's called a Geiger counter. And the use of a Geiger counter will be a part of our experiment 1. So the way a Geiger counter works is you have a argon-filled wand here, and when the radiation enters it, it knocks loose electrons on the argon, and those electrons travel towards a positive electrode, and when they hit it, uh, it makes a electrical signal, and often that's translated to like a noise, click, 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 click. So when you see it on the TV shows, it sounds like click, 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 click. Each one of these events is registered, so it's pretty neat. You can detect individual radiation events and count them because often they're pretty rare, even with a large sample. You're going to see that in our experiment 1 about potassium 40. So the technical name and the SI unit for a decay event or a disintegration of a nucleus is a becquerel. It stands as for the rate of radioactivity. It stands for 1 disintegration per second, or one decay event per second. And this is also related to to a more commonly used measurement, which is called a Curie. A Curie is 3.7 times 10 to the 10 disintegrations per second, so a more reasonable amount. Obviously, 1 is very small for a whole like bunch of atoms. The remaining, so I put a box around these because these ones are the ones I want you to be able to use. I would provide you with this conversion factor, but I want you to be aware of their definitions. For the rest, these are related to biology and the radiation energy that's absorbed per kilogram of body mass, the resulting tissue damage that may occur. So you don't have to memorize these, but you can see there's a lot of different ways of measuring radiation here. But these are the ones, we would mostly use as physical scientists. These are more related to biology. So some properties of radiation here. First, a big one is, what can the radiation get through? So alpha particles, actually, your own skin can protect you from them. They cannot penetrate more than 0.02 millimeters in water. Of course, you're mostly water. So the only way that people get exposed to alpha particles is if they breathe in the radioactive material. That's why radon is a concern, because radon occurs as a noble gas, and so it can be breathed in, and if it's radioactive radon, it can undergo nuclear decay inside of your body. For which then you wouldn't have any protection. Beta particles can penetrate further into water. So suitable protection for beta particles is like a thin piece of metal would be enough to protect from beta particles. X-rays, which are a type of electromagnetic radiation, these can go through a significant distance of water. That's why when you go to get an X-ray at the hospital or something, or the dentist, they put a lead coat over you because the lead can protect you from the X-rays. A lead or thick concrete blocks can protect from gamma rays, but they can penetrate through water quite deeply. And they're the highest in energy and the most harmful. In space, there's lots of gamma rays, so part of the protective suit of astronauts is protection from those gamma rays. So the biological effects of radiation are stated in terms of the REMS. So if we go back here, REMS is related to the sievert. The sievert is a joule of energy per kilogram absorbed. So this generally, a dosage of radiation in medical terms is prescribed as so many REMS. So just sitting in your room right now, you're probably being exposed to maybe a quarter REM, and you're always exposed to that, so you'll have no detectable effects. Of course, things can happen. It can lead to damage of the DNA, but even just just regular radiation. This is why cancer can happen to anyone, anytime. It's kind of a luck of a draw, because there's radiation all around. It's just not enough to really cause any damage most of the time, except in rare extreme circumstances where a DNA edit cannot be corrected. So it's very, very uncommon. Uh, higher than 25 rems will have some noticeable effects. Higher than 100 to 200 will be nausea, vomiting, as you can see here. Higher than 200 and 300, you're getting very serious effects. 300 or more is the range in which you could die, and above 600 is certain death for radiation exposure. But it's important to note that we're always exposed to radiation. There's radioactive material all around. That's just part of the world. But unless it's very high dose, it's not a big deal. So the next topic we're going to talk about here is some applications of nuclear chemistry, including including talking about the time that it takes for nuclear events to happen and how that is used, and also how nuclear reactions are used in the medical field. So one important use of nuclear chemistry is in the radioactive carbon dating of formerly alive organisms that died. We can find when they died based on the amount of radioactive carbon-14 remaining in their bodies. So here is a picture of a mummy that can be dated for when it died using radioactive carbon dating. Remember that carbon undergoes beta decay, produces nitrogen-14. That was one of our early examples. Now, radio decay follows what's called first order rate law. So we're going to be talking more about rate law when we get to the next chapter, chapter 16. But a rate is defined by a change in the case of nuclear reactions, a change in the number of radioactive atoms divided by the change in time. The D here means a change. And it is described by a rate constant times the number of radioactive atoms to the first power. That's what it means for it to be first order rate law. And we'll go into more detail about this in chapter 16. If you want to relate the number of radioactive atoms, or the activity versus time, you need to do a mathematical operation called integration of this. And I'll kind of demonstrate that. For those of you that have had calculus, I'll show you in chapter 16 how that works. But the result of integration from time 0 to a certain time t gives us this formula, which I'll provide you if you need it. But it says the natural log of the radioactive material at time t divided by the radioactive material at time 0, the initial radioactive material, equals the negative of the rate constant times the temperature. Or sorry, not the temperature, the time that has passed. Often, the amount of time that it takes for a substance to undergo radioactive decay is given by its half-life. A half-life means the time it takes for half of the radioactive material to have already decayed. And the way that you get this, I can show you the math here real quick, is that if we're talking about the half-life, what we mean is the n at time t is half of the initial amount. So if we plug half of the initial amount for n of t, we get natural log of half of the initial amount over the initial amount, and this is natural log of all of this, equals negative kt. So this is the I'll continue down here, and right here these cancel, and so you get the natural log of 1/2 equals negative kt. If we multiply both sides by -1, we get negative natural log of 1/2 equals kt. And then remember, this would be log rule C3 from the algebra review I gave you last week. If you have something, this is -1 times a log, you can put that as a power. So this would be natural log of 1/2 to the -1 power. And when you take something to the -1 power, what you're really doing is inverting the fraction. So this is the natural log of 2, which equals kt. And then if you divide both sides by k, you get natural log of 2 over k equals the time. And this is the time we're talking about here now is the half-life, which we call T1 half. So we get T1 half, T1 half. This is a particular time, the half-life. And so that's where this formula comes from. And we're going to use this formula in the next problem. This little exercise I did, I highly recommend you repeat this exercise yourself. Practice. This is a very good algebra practice for you. The truth is, like I said, I don't memorize a lot of these equations. I'll remember them again if I use them a lot, and I use this one a lot, so I basically have it memorized. But if back in the past when I was out of chemistry for a while, I was still able to get back to this because I knew how to do the math, and that really helps you in keeping your knowledge fresh by just being able to get from a basic principle here. Later on, if you have calculus, I'll show you how you can get from this to this. Actually, I don't even have this memorized sometimes. I just know I can get it. Okay, so here's an example of a kinetics problem having to do with nuclear reactions. So phosphorus 32 is used for chemotherapy for leukemia. It has a half-life of 14.26 days. What percent of the sample remains after 35 days? Okay, what we're going to need is the rate constant, because let's write out the equation we're going to use. We're going to use the natural log of nt over n0 equals minus kt. This is the equation we use to determine how much of a radioactive sample is remaining after a certain amount of time. Now, what we want actually is we want what percent of the sample. So we want this ratio turned into a percent. So what we can do is we can take e to the power of both sides. Now remember, e cancels the natural log. So this is going to cancel the natural log. See why I had to do the algebra review last week? And that will give us nt over n0, which is actually what we want. This is going to be e to the minus kt. However, we need the k. So we can get the k in this way. We had the equation that the natural log of 2 over k equals T1 half, the half-life. So if we multiply both sides times k, and we divide both sides by T1 half, we're going to multiply both sides by k, divide by both sides by T1 half. Then our k's on this side will cancel, and our T1 halves on this side will cancel. And we'll get that k, so that's what's right here, that's left here, k equals natural log of 2 over the half-life. And so this is going to be the natural log of 2 over 14.26 days. So k is going to equal, and so now let's punch this into our calculator. It's going to be, now I have a single line calculator, so I have to hit 2 first, and then I hit natural log. If you have a double line calculator and you hit, this is how you'll know if you have a double line calculator. If I hit natural log, it will say invalid. If you hit natural log and yours shows you on the screen natural log, then you're good. For me, I have to hit 2 and then hit natural log because it's a single line calculator. So then I get the result. So that's the natural log of 2. Now I divide it by 14.26 equals. And so I get that my k is 0.0486. 0.486, and I should probably keep one more. 1. And my units are 1 over days, or days to the minus 1 power. 1 over day. You could also call that day to the minus 1 power. So now I can plug this into here, so I'll get nt over n0 equals e to the minus, and my k is 0.04861, 1 over days, times the time that passed, which is 35 days. And so nt over n0 is going to equal, so on my calculator here, I'm going to, again, I've got a single line calculator, so I have to multiply what's in the top first. If you have a double line calculator, you can just type it all in with the e and everything. But for me, I'm going to put what's in the top first, so it's going to be 0.04861, and that's going to be negative, times 35. And then I want to take e to the power of that, so I do e. Oops. E to the, oh man, I had to write it out, I guess. So I'm gonna do e to the power of, was it 0.04861 times 35. So e to the power of negative 1.701. And so now I'm going to do e to the power of 1.701, make that a negative, and I get 0.183. 0.183. And I want this as a percentage, so if I want to make it a percentage, I multiply times 100%, and that gets me 18.3%. There's 18.3% remaining at the end. So this is going to be your first exposure to doing kinetic problems like this. We're going to be doing a ton of these in chapter 16. But it turns out that we're going to have other orders. So nuclear decay processes are always first order. And we talked about at the beginning how nuclear decay processes do not depend on the amount of radioactive material you have for their speed. That's true for all first order processes, but it's not true for others that we'll talk about in chapter 16. Finally, nuclear chemistry is used significantly in medicine for various diagnostic procedures and imaging procedures, also chemotherapy. So here are some various radioactive isotopes that are used in the medical field. Fluorine 18, as we mentioned earlier, is used in positron emission tomography. And phosphorus 32, we used as an example earlier for leukemia chemotherapy. Cobalt 60 is also used for chemotherapy. Technetium 99 is used for certain brain scans and imaging. And iodine 123 is used for thyroid therapy because the thyroid has by far the highest concentration of iodine in the body. So if you inject someone with iodine, it will go into their thyroid, and they use it for imaging studies of the thyroid and for therapy of the thyroid. So that's the end of our study of nuclear chemistry. I hope this has been pretty interesting to you. I actually really like this chapter a lot. And so go ahead and make sure you're keeping up with the homework. There's going to be a discussion this week where you will make up a nuclear decay problem and solve one with the other students. And of course, there will be the quiz. And the lab assignment this week is going to be starting on exercise A. So about the middle of the week, I'll start helping with that. I'll probably make another video to kind of help you get on with that. But anyway, thanks for watching, and I'll see you in office hours.